Hello, friends. Welcome back to my YouTube channel. Uh, this is 15th part of my discussion on liquid extraction, and I will continue my discussion on stage-wise liquid extraction with insoluble liquids. So, since part number 13 and 14, I have started discussing liquid extraction involving insoluble liquids. So, in this case, in the ternary system of liquid A, B, and C, A plus C is the feed and B is the extracting solvent. So, in this case, A and B, they are insoluble in each other, completely insoluble, not at all soluble in each other. A and B, they are not at all soluble in each other. In the previous discussions, we had considered A and B to be partially soluble. But now we are discussing the case where A and B, they are not at all soluble in each other. So I'm calling those liquids A and B, as insoluble liquids. So in part number 13, I discussed how to represent the ternary equilibria when you have such insoluble liquids. And part 14, I discussed single stage. Actually, in part 14, I had discussed one numerical based on single stage extraction involving insoluble liquids. And in part number 13, I had discussed the theoretical aspects of single stage extraction with insoluble liquids. So I'm giving link to the playlist that has all my videos on liquid extraction in the description section. You please watch it. Now, today, we will continue our discussion on this system, insoluble liquids, stage-wise liquid extraction. And today, I'll be discussing multistage cross-current liquid extraction. So we will understand how to take material balance, then how to represent the material balance on the equilibrium diagram. In the case of multistage cross-current liquid extraction, that involves insoluble liquids. That involves A and B that are not at all soluble in each other. So, at the end of today's discussion, you'll learn how you can write material balance for this operation, multi-stage cross-current liquid extraction. I have discussed a 3-stage cross-current liquid extraction operation. You'll learn how to plot the operating lines on the equilibrium diagram. So let us start the discussion. First of all, we will briefly understand what is stage-wise contact. So stage-wise liquid extraction, in this case, the two insoluble liquid phases, that is feed solution and the solvent, they are contacted in a stage-wise manner. And therefore, it is carried out in stage-wise contact equipment. It is carried out in equipment where stages are provided in which the two insoluble liquid phases, feed solution and the solvent phase, they can be contacted with each other. So, especially in the case of liquid extraction, each stage in the stage-wise contact equipment, it should have a provision to intimately mix the two insoluble liquid phases, feed and solvent. So, in all stage-wise equipment that are used for carrying out liquid extraction, stage-wise liquid extraction, there are number of stages, and each stage has a provision to intimately mix the two insoluble liquid phases, feed and solvent. And the stage also has a provision to physically separate the resulting raffinate and extract phases. So after the feed and solvent, they are mixed together. When they are intimately mixed together, a mixture will be formed, and then the mixture, when allowed to settle, it will separate into raffinate and extract phases. So the stage should also have a provision to allow the resulting mixture to separate into two layers, and then those separated layers, that is raffinate and extract layers or raffinate and extract phases, then they are physically separated from each other. So there is also provision for their physical separation. So in short, every stage in the stage-wise contact equipment that is used for carrying out stage-wise liquid extraction, it has a provision to intimately mix the two insoluble liquid phases, feed and solvent, and it also has a provision to allow the resulting mixture, when you mix feed and solvent, to settle and then separate into two layers. And then after separation has occurred, the two layers can then be physically separated. There is provision to physically separate those raffinate and extract phases. And therefore, since we need this intimate mixing and physical separation, each stage in the stage-wise contact equipment that is used for liquid extraction, each stage is constituted of a mixer and a settler. So the combination of these two, mixer and settler, it forms one stage in this equipment. So we can show it schematically. So you have the mixer, which is followed by the settler, and this combination forms a stage. Feed is admitted into the stage. Solvent is also admitted into the stage. Feed and solvent, they will be intimately mixed in the mixer, and then the resulting mixture is transferred to a settler, where it will settle into two layers, and those which are those two layers, raffinate and extract phases. Then those two layers will be physically separated from each other. So you have the raffinate phase, and then you have the extract phase. So this is how a stage in a stage-wise contact equipment that is used for liquid extraction, it works. As per requirement, you can use multiple stages in the operation. So if multiple stages are required, you can use multiple stages, and these multiple stages, you can arrange them in a desired cascade. You can arrange those multiple stages in a desired cascade. What is a cascade? Cascade of multiple stages. It is multiple stages in a cascade of multiple stages. The multiple stages are arranged so that an output from one stage is an input to the next stage. So they are arranged in such a way that output from one stage is input to the next stage. So when you have this arrangement is called a cascade. So that's why we are understanding cascade of multiple stages as an arrangement where multiple stages are arranged so that an output from one stage is an input to the next stage. So I had shown the diagram. We will understand. I'll shortly show you the schematic diagram. Two common cascades that are used for liquid extraction, for stage-wise liquid extraction. You have cross-current cascade and counter-current cascade. And today I'm going to talk about cross-current cascade. So when you carry out liquid extraction in cross-current cascade, you have multi-stage cross-current liquid extraction. Why multi-stage? Because you are using multiple stages and you are carrying out the operation in a cross current cascade. So it is multi-stage cross current liquid extraction. In cross current operation, what is done? The raffinate phase is successively contacted with fresh solvent in multiple stages. So in raffinate phase moves from one stage to the other, whereas in each stage the raffinate phase is contacted with a fresh solvent. I will show you the schematic. So for time being, you just understand in cross current liquid extraction, the raffinate phase is successively contacted with fresh solvent in multiple stages. You can carry out this operation either batch wise or in a continuous manner. Now let us look at a 3-stage cross current liquid extraction, because I will be discussing 3-stage cross current liquid extraction. First of all, let us look at the schematic diagram. Before looking at the schematic diagram, let us know the system that we will be considering. The ternary system that is involved in this case has 3 components, A, B and C. All 3 are liquids. C is soluble in both A and B. It is the solute. But in this case, A and B, they are insoluble in each other. Or in other words, let me say it like this: A and B, they are not at all soluble in each other. In my earlier discussion, I had considered a case where A and B, they are partially soluble in each other. But now we are considering A and B to be insoluble in each other. They are not at all soluble in each other. Then the feed solution in this case is solution of A and C, where C is the solute to be recovered. The solvent used in this case is B. If it is pure, then it will be just B. But if you are using a recovered solvent, then it will be containing little amount of C in it. So it will be B plus C, where C is in little quantity. When this is true, if you are using a recovered solvent. Then the feed solution and the solvent, they are mixed together, they are contacted with each other, in a 3-stage cross current liquid extraction operation. 3-stage cross current operation. Again, you can carry out it in a batch wise manner, or you can carry out it in a continuous manner. Now let us look at the schematic diagram. So there are 3 stages: stage 1, stage 2 and stage 3. Feed is admitted to stage 1. So I'll shortly tell you of what is EF, what is XF, small xf, what is capital XF. And this feed is contacted with solvent. S10, YS and capital YS, I'll tell you. This is contacted with solvent. So when the operation is completed in stage 1, the raffinate phase will be removed and it will be going to stage number 2. You please remember, since in this case A and B, they are not at all soluble in each other, all A will remain in the raffinate phase, whereas all B, it will go in the extract phase. So feed consists of A and C. You are contacting it with B or B plus C if it is a recovered solvent, and then all B will go in the extract phase and all A will go in the raffinate phase. Why so? Because this is a system where A and B, they are not at all soluble in each other. Then the raffinate obtained from stage number 1, it is sent to stage number 2, where it is contacted with a fresh batch of solvent. So at the end of operation in stage 2, raffinate phase will come out. It will contain all A in it, and then it will be sent to stage number 3. Extract phase will come out of it. Extract phase will contain all B in it. All B will remain in the extract phase, whereas all A goes in the raffinate phase. Raffinate phase from stage number 2, it is sent to stage number 3, where it is again contacted with a fresh batch of solvent. After extraction is completed, you get raffinate phase out of stage number 3, which will have all A in it, and the extract phase that is obtained from stage number 3, it will have all B in it. So that is the extract phase that you get from stage number 3. Now let us understand the notations that I have used in this schematic diagram. So for feed, F is its mass or mass flow rate. If you are considering a batch operation, it would be mass of feed, and if you are considering a continuous operation, it would be mass flow rate. Then small xf is weight fraction of C in the feed, and capital XF is weight fraction of C on a C-free basis. So I have discussed these concentrations in part number 12 of my lecture series on liquid extraction. You please watch it if you have not yet seen that video. It is there in the playlist, for which I have given a link in the description section. So feed is described by this. F, the mass flow rate or mass, XF weight fraction, capital XF weight fraction of C on a C-free basis. Then the solvent that you use in this operation. So you are using solvent in fresh solvent in each stage. So fresh solvent is admitted to stage 1, fresh solvent is admitted to stage 2, and fresh solvent is admitted to stage 3. So in this case, this S10, S20, S30, these are masses or mass flow rates of solvents, depending on whether it is a batch operation or a continuous operation. So S10, solvent going to stage number 1, S20, solvent going to stage number 2, S30, solvent going to stage number 3. Then Ys is weight fraction of C in the solvent. It will be there if you are using a recovered solvent. If you are using a fresh solvent, then Ys will be equal to 0. Then capital Ys is weight fraction of C on a C-free basis in the solvent. Then the raffinate phase. Raffinate phase, you have raffinate phases coming out of each stage, R1 from stage 1, R2 from stage 2, and R3 from stage 3. So R1, R2 and R3 in this case, these are masses or mass flow rates of raffinate that comes out from respective stages. X1, small x2 and small x3, these are weight fractions of C in respective raffinate phases, whereas capital X1, capital X2 and capital X3, these are weight fractions of C on a C-free basis and the respective raffinate phases. And let us know about the extract phase. E1, E2, E3, these are masses or mass flow rates of extract phases coming out of stage 1, 2 and 3 respectively. Small y1, small y2 and small y3, these are weight fractions of C in the extract phases coming out of stage 1, stage 2 and stage 3 respectively. Capital Y1, capital Y2 and capital Y3, these are weight fractions of C on a C-free basis in the extract phases coming out of stage 1, 2 and 3 respectively. So these are the notations that we will be using in our discussion. Let us start with stage number 1. So I have shown it separately. So you are mixing feed, you are admitting feed to stage 1. It is contacted with solvent, and after the extraction is completed, raffinate phase is removed out of it and extract phase is removed out of it. Raffinate phase will be containing all A in it, extract phase will be containing all B in it. All A will remain in the raffinate phase, all B will remain in the extract phase. Why? Because A and B, they are not at all soluble in each other. So for doing calculations for stage number 1, what is known to us? Feed is known, mass of the feed or mass flow rate of the feed is known to us. The weight fraction of solute in the feed is known to us. and therefore capital XF is also known. Then S10, that is mass or mass flow rate of solvent that is admitted into stage 1, that is also known to us. And YS, that is weight fraction of C in the solvent going to stage number 1, it is also known to us. You must have seen YS is same for all the 3 stages. So this suggests that you are using the same solvent, but different in different quantities. You are admitting a different quantity of solvent in stage 1, another quantity of solvent in say stage 2, and some different quantity of solvent in stage 3. Quantities could be different. Quantities admitted to individual stages, they could be different or they may be same. But since you are using the same solvent, its composition will be same for all the stages. So that's why weight fraction of C in the solvent that is admitted to all the stages, it is YS. So for doing calculations for stage 1, we know the feed, mass flow rate, weight fraction of C in the feed, solvent mass flow rate, and weight fraction of C in the solvent. Now let us take the steady state total material balance for stage 1. So feed and solvent, they will be mixed. Initially a mixture will be formed, and then this mixture will separate into raffinate and extract phases. So mass of feed plus mass of solvent is equal to mass of the resulting mixture, which then separates into raffinate and extract phase. So mass of mixture is equal to mass of raffinate plus mass of extract, and I am calling this as equation 1. Then I will write steady state material balance for the solute C. So it will be F into XF, that is total feed into fraction, F into XF plus S10 into YS is equal to M1 into XM1, where M1 is mass of the mixture and XM1 is weight fraction of C in the mixture, is equal to R1 into X1 plus E1 into Y. So C in feed plus C in solvent is equal to C in the resulting mixture, which then separates into raffinate and extract phase. Therefore, it will be equal to C in the raffinate phase plus C in the extract phase. And I am calling this as equation number 2. And now the feed solution in, that is admitted to stage number 1, it will contain A and C in it. We know that feed contains A and C in it, and that is feed, mass of feed is equal to mass of A plus mass of C. That is mass of F, mass of feed, F is equal to A. And how do you get mass of C in the feed? Weight fraction of C in the feed into total mass of the feed. So this is F is equal to A plus XF into F. So in the next step, I will bring this term to this side. So it will be F minus XF into F, that is equal to A. Now I can take F common out of this 2. So it will be F into 1 minus XF, that is equal to capital A. In the next step, I will bring this term on this side. So it will be F is equal to 1 upon 1 minus XF into A. Then I will multiply on both the sides with XF. So it will be F into XF, that is equal to XF upon 1 minus XF into A. But this is nothing but, that is XF upon 1 minus XF. Small xf divided by 1 minus small xf is capital XF, which is weight fraction of C on a C-free basis. So the relation between weight fraction and weight fraction on solid-free basis, you have this relationship. I have discussed this relationship in part number 12 of my lecture series on liquid extraction. Therefore, F into XF will be A into XF. That is, at the end, I can replace this term F into XF with this term A into XF. Now let us look at the solvent. Solvent will be containing B1 and C in it. Why B1? Because we are talking about the solvent that is admitted into stage number 1. So if it is a recovered solvent, it will contain C. If it is pure solvent, it will just contain B1. So let us consider that it is a recovered solvent. Therefore, mass of solvent will be equal to mass of the solvent. It will be mass of B1 plus mass of C. That is, mass of S10 is equal to B1. And how do you get mass of C in the solvent? It is Ys into S10. So now I can bring this term to this side. So it will be S10 minus Ys into S10, that is equal to B1. Now I can take S10 common. So it will be S10 into 1 minus Ys, that is equal to B1. And if I bring this term on this side, it will be S10 is equal to 1 upon 1 minus Ys into B1. Then when I multiply on both the sides with Ys, it will be S10 into Ys, that is equal to Ys upon 1 minus Ys into B1. But Ys upon 1 minus Ys is capital Ys. That means S10 into Ys, it can be replaced with B1 into Ys, which we will be doing it at the end of our discussion for stage number 1. So S10 into Ys in this particular equation, that is equation number 2, it can be replaced with the term B1 into Ys. Now let us look at the raffinate phase. Raffinate phase, it will contain A and C. As I said, all A will be remaining in the raffinate phase. So that is mass of raffinate is equal to mass of A plus mass of C. That is R1 is equal to A and mass of C, and it is X1 into R1. So if I bring this term to this side, it will be R1 minus X1 into R1, that is equal to A. Now I can take R1 common. So R1 into 1 minus X1 is equal to A. Then I'll bring this term on this side. So it will be R1 is equal to 1 upon 1 minus X1 into A. And if I multiply with X1 on both the sides, it will be R1 into X1, that is equal to X1 upon 1 minus X1 into A. But X1 upon 1 minus X1 is capital X1. That means R1 into X1 is A into capital X1. So that means I can replace R1 into X1 in equation number 2 with A into X1. Okay, now let us look at the extract phase. The extract phase will contain B1 in it and C in it. That means mass of extract is equal to mass of B1 plus C, mass of C. That is E1 is equal to B1 plus Y1 into E1, because C in the extract phase is Y1 into E1. Then I'll bring this term to this side. So it will be E1 minus Y1 into E1, that is equal to B1. Then E1 can be taken common. So E1 into 1 minus Y1 is equal to B1. Therefore, when I bring this term to this side, it will be E1 is equal to 1 upon Y1 into B1. Then let us multiply on both the sides with small y1. So it will be E1 into Y1, that is equal to Y1 upon 1 minus Y1 into B1. But Y1 upon 1 minus Y1 is capital Y1. That means E1 into small y1 can be replaced with B1 into capital Y. And that we are going to do at the end of our discussion for stage number 1. So for stage number 1, we have got this relationship. Fxf is A into xf. F into small xf is A into capital xf. S10 into small ys is B1 into capital Ys. R1 into small x1 is A into capital X1. And E1 into small y1 is B1 into capital Y1. So we have obtained this relationship in our previous discussion. Now we are going to use this in equation number 2. So equation number 2, if you use all this, it becomes A into xf plus B1 into ys, and that is equal to A into x1 plus B1 into y1. So now what I will do, I will bring A into x1 on this side and take B1 into ys to the other side. So it will be A into xf minus A into x1, that is equal to B1 into y1 minus B1 into ys. And the next step, you can take A common, so on this side, so it will be xf minus x1 into A. And on this side, you can take B1 common. So it will be Y1, capital Y1 minus capital Ys into B1. Then you can write A1, A upon B1 is equal to Y1 minus Ys divided by XF minus X1. Now let us continue with this. So we got this equation, A upon V1 is equal to Y1 minus Ys divided by XF minus X1. So on a XY plot, this equation is a straight line. It is a equation of a straight line which has endpoints of XF and the other endpoint is X1 Y1. Now, in order to let us make it, this is point number 1 and this is point number 2, N2. So let us have 2 minus 1, where coordinates of point 2 are separated from the corresponding coordinates of point 1 are subtracted from corresponding coordinates of point 2. So for that, in the numerator, if you look at the numerator on this side, it is Y1 minus Y2. That is y coordinate of point 2 is subtracted from y coordinate of point 1. Now let us make the same situation. Let us arrange the term in the denominator in the same way. So point number 2, x coordinate at point 2 minus x coordinate at point 1. So I have to make x1 minus xf. And in order to make that, I'll have to take minus sign common. That is, I will have to arrange the equation. The equation is rearranged to get this. Minus a upon b1 is equal to capital Y1 minus capital Ys divided by capital X1 minus capital Xf. So this is nothing but equation of the operating line for first stage. So for this operating line, the operating line passes through these 2 points, point number 1 and point number 2, and it has a slope of minus a upon b1. So we will be using the slope to plot the operating line for stage number 1. So let us show the operating line. So you have the graph, capital Y you are plotting on y-axis and capital X you are plotting on x-axis. We will be getting the equilibrium curve. Then one end of the operating line, XF, Ys. XF is known to us, Ys is known to us. That is, point 1 can be fixed. So for that, I will have to locate Ys and locate XF. And the point whose coordinates are XF, Ys, that will be the starting point for my operating line. And then I'll have to draw the operating line from this point with a slope of minus a upon b1. So this is the operating line for stage 1. It starts at XF, Ys, this point. And let me tell you, if you are using pure solvent, Ys will be 0. In that case, operating line will start on the x-axis at XF. So that is true if Ys is 0, that is you are using pure solvent. The other end of the operating lines, we will be getting it at the intersection point of the operating line with the equilibrium curve. Because at the end of operation in stage number 1, the two phases are going to equilibrium. They will be in equilibrium with each other. Under ideal conditions, they will be in equilibrium with each other. And that's why the other end point of the operating line, it will lie on the equilibrium curve. So we are interested in knowing the coordinates of this point. The x coordinate of this point is nothing but x1 and y coordinate of this point is nothing but capital Y. So at the end of calculations for stage 1, what do we get? We get the values for x1 and y1. By plotting the operating line for stage 1, we are getting the point where it intersects the equilibrium curve, where the operating line intersects the equilibrium curve. and that point has coordinates of x1, y1. So I hope it is clear to you how to plot the operating line for stage 1. Okay, now after stage 1, let us look at stage 2. So I am showing the stage 2. For stage 2, feed is the raffinate phase that is coming out of stage number 1. And this raffinate phase, it is contacted with fresh solvent. Quantity may be different, but composition is same. So the raffinate out of stage number 1, it is contacted with fresh solvent, and at the end of operation in stage 2, you get raffinate phase out of stage number 2, which will have all A in it, and you will get extract phase out of stage 2, which will have all B in it. Why so? Because we are considering the case where A and B, they are not at all soluble in each other. So before we start calculations for stage 2, what quantities are known to us? R1 is known from the previous calculations. Small x1 is known. S20 is known, and Ys is known. So all that is required for doing calculations for stage number 2, all those quantities are known to us. Okay, so first let us take steady state total material balance. So in stage number 2, raffinate from stage 1, R1 is mixed with fresh solvent. So it will be R1 plus S20 is equal to M2, which is the mass of the resulting mixture, which will then separate into raffinate and extract phase. So mass of mixture is equal to R2 plus E2. I am calling it as equation 3. And then we will write steady state material balance for C. It will be R1 into X1 total into fraction plus S20 into Is, that is equal to M2 into XM2, mass of the mixture and weight fraction of C in the mixture in stage 2, that is equal to R2 into X2 plus E2 into Y2. Okay, now we will, as we did for first stage, here also we will be analyzing all the 4 streams associated with stage number 2. Let us start with the feed solution. As I said, feed solution to stage number 2 is the raffinate that comes out of first stage. And it will be containing A and C in it. And we have previously shown that R1 into small x1 is R1 into capital X1. Now let us look at the solvent. Solvent, it contains B2 and C in it. B2, since the solvent is admitted to stage 2, so it will be containing B2 and C. Therefore, S20, mass of solvent, is equal to mass of B2 plus C. That is S20 is equal to B2 plus Ys into S20, because that is nothing but mass of C in the solvent. And I will bring this term on this side. So it will be S20 minus Ys into S20, that is equal to B2. Then S20 can be taken out as a common term. So S20 into 1 minus Ys, that is equal to B2. And when I bring this term to the side, it will be S20 into 1 upon 1 minus Ys into B2. And then I will multiply on both the sides with Ys. So it will be S20 into Ys, that is equal to Ys upon 1 minus Ys into B2. But small Ys upon 1 minus small Ys is capital Ys. That is S20 into Ys is B2 into capital Ys. That means in equation number 4, the term S20 into Ys can be replaced with B2 into capital Ys. Okay, now let us look at the raffinate that comes out of stage number 2. So it will be containing A and C in it. And then mass of raffinate will be mass of A plus mass of C. That is R2 will be equal to A plus X2 into R2, mass of C in raffinate. Then I'll bring this term to this side. So it will be R2 minus X2 into R2 is equal to A. And R2 can be taken common. So it will be R2 into 1 minus X2 is equal to A. Then 1 minus X2 I'll bring on this side. So it will be R2 is equal to 1 upon 1 minus X2 into A. That is and if I multiply on both the sides with x2, it will be r2 into x2, that is equal to x2 upon 1 minus x2 into a. But x2 upon 1 minus x2 is capital X2, which means r2 into small x2 is a into capital X2. That is r2 into x2. This term in equation number 4 can be replaced with the term a into x2. Now let us look at the extract phase. Extract phase, it contains B2 and C in it. That is mass of extract is equal to mass of B2 plus C. That is A2 is equal to B2 plus Y2 into E2. And then this term is taken on this side. So it will be E2 minus Y2 into A2 is equal to B2. Then E2 is taken out as common term. So A2 into 1 minus Y2 is equal to B2. And when this term is brought on this side, it will be E2 is equal to 1 upon 1 minus Y2 into B2. If I multiply with Y2 on both the sides, it will be E2 into Y2. That is equal to Y2 upon 1 minus Y2 into B2. But Y2, small y2 upon 1 minus y2 is capital Y2. That means E2 into small y2 is equal to B2 into capital Y2. That is E2 into Y2 in equation number, it can be replaced with B2 into capital Y2. Okay, so now for stage 2, we have this equations. R1 x1 is equal to A into capital X1. S20 into small ys, that is equal to B2 into capital Ys. R2 into small x2 is equal to capital A into capital X2. And E2 into small y2 is equal to B2 into capital Y2. Now, we will use these relations in equation number 4. So, equation number 4 becomes A1 into capital X1 plus B2 into capital Ys, that is equal to A into capital X2 plus B2 into capital Y2. In the next step, I will bring this term to this side. So it will be A into X1 minus A into capital X1 minus A into capital X2, that is equal to B2 into capital Y2 minus B2 into capital Ys. And if I take A common on this side, it will be capital X1 minus capital X2 into capital A, that is equal to capital Y2 minus capital Ys into B2. And if I rearrange it, I will get this equation. A upon B2 is equal to capital Y2 minus capital Ys divided by capital X1 minus capital X2. Okay, so we got this. A upon B2 is equal to capital Y2 minus capital Ys divided by capital X1 minus capital X2. And this is on the XY plot. It is a straight line, equation of a straight line, and endpoints of this straight line are x1 ys and x2 y2. So if this is end 1 and this is end 2, then we need to arrange the equation. We need to arrange this equation in such a way that coordinates of end 2 are subtracted from coordinates of end 1. So in order to do that, we will have to rearrange it. So in the numerator on this side, this is capital Y2 minus capital Ys. So in the denominator also, we need to make it capital X2 minus capital X1. So for that, I will have to take negative sign common. And if I do this rearrangement, after rearranging the equation, I get minus A upon B2 is equal to capital Y2 minus capital Ys divided by capital X2 minus capital X1. Now, let us, this is nothing but the operating line for stage 2, and it has endpoints. One endpoint is X1 capital Ys, whereas the other endpoint is X2 capital Y2, and it has a slope of minus, slope of this line, slope of the operating line for stage 2 is minus A upon B into B minus A upon B2. Now let us represent this line on the XY plot, that is equilibrium diagram. So here I will take the diagram that we had drawn at the end of our discussion for stage 1. So this is the line. So the operating line for second stage should start at this point, because the raffinate from stage 1 is feed to the stage 2. So the operating line for stage 2 should start, or it will start at this point, because this end of the operating line, one end of the operating line is x1, ys, and this is the point which has this coordinates. So the operating line for second stage will start at this point, and it will be drawn with a slope of minus a upon b2, the slope of the operating line for second stage, and this line will go on and intersect with the equilibrium curve. Ideally, this should happen because the raffinate and extract phase that leave stage number 2, they will be in equilibrium with each other. So we get this point, and the coordinates of these points will give us x2 and capital X2 and capital Y2. So at the end of our calculations for stage 2, we have got values for x2 and y2. That's complete. That completes our calculation for stage 2. Now we will move on to stage number 3. So let us do that. So now you have operating line for stage 1, operating line for stage 2. At the end of our calculations for stage 2, we now know the values of capital X2 and capital Y2. Now let us look at stage number 3. So this is stage number 3. For stage number 3, the raffinate from stage number 2 is the feed. It is contacted with fresh solvent, and then at the end of the operation in stage number 3, you are going to get raffinate out of it and extract out of it. Raffinate will contain all A in it, and extract will contain all B in it. Why? Because in our discussion, A and B, they are not at all soluble in each other. So before we start our calculations for stage number 3, which quantities are known to us? Let us list them. We know R2, we know X2, small x2 and capital X2. We know the quantity of solvent that is added to stage 3, that is S30, and we also know the composition of the solvent, that is Ys. So if you write steady state total material balance for stage number 3, it will be written as R2 plus S30, that is equal to M3, that is equal to E3 plus R3, and I am calling this as equation number 5. So raffinate from stage 2 is mixed with fresh solvent to get a mixture. The mixture is then separating into raffinate and extract phases. So the equation is R2 plus S30 is equal to M3, that is equal to R3 plus E3. Then if you write steady state material balance for C, it will be written as R2 into X2 plus S30 into Ys plus M3 into XM3, that is equal to R3X3 plus E3Y3, and I am calling this as equation number 6. Now feed solution, feed to stage number 3 is the raffinate that is obtained from second stage, and it will be containing A and C in it, and previously we got this relationship, capital R2 into small x2, that is equal to A into capital X2. Now let us look at the solvent that is added to stage number 3. So it contains B3 and C, and therefore S30 will be equal to B3 plus C, and that is S30 is equal to B3 plus Ys into S30, because C in this solvent is given as Ys into S30. That is S30 minus Ys into S30 is equal to B3. And if I take S30 common, so it will be S30 into 1 minus Ys is equal to B3. That is, if I bring this term to this side, it will be S30 is equal to 1 upon 1 minus Ys into B3. And if I multiply with ys on both the sides, it will be S30 into ys, that is equal to ys upon 1 minus ys into B3, and ys, small ys upon 1 minus small ys is capital Ys, that is S30 into ys is nothing but B3 into ys. That is in equation number 6. The term S30 into ys, it can be replaced with B3 into capital Ys. Now let us look at the raffinate phase. Raffinate phase, it will contain A and C in it. So R3 in this case is A plus C. Mass of raffinate is equal to mass of A plus mass of C. That is R3 is equal to A plus X3 into R3, because C in the raffinate phase is X3 into R3. If I bring this term to this side, it will be R3 minus X3 into R3, that is equal to A. If R3 is taken out as a common term, it will be R3 into 1 minus X3, that is equal to A. That is R3. If this term is brought on this side, it will be R3 is equal to 1 upon 1 minus X3 into A. Then I'll multiply with X3 on both the sides. So it will be R3 into X3, that is equal to X3 upon 1 minus X3 into A. But X3 upon 1 minus X3 is capital X3. That is R3 into small x3 is capital X3 into A. That means R3 into X3 in equation number 6, it can be replaced with X3 into A. Now let us look at the extract phase. Extract phase contains B3 and C in it. That is E3 is equal to B3 plus C. That is E3 is equal to B3 plus Y3 into E3, because C is Y3 into E3 in the extract phase. Then if this term is brought on this side, it will be E3 minus Y3 into Y3 into E3, that is equal to B3. Then E3 can be taken out as common term. So E3 into 1 minus E3 is equal to B3. This term is brought on this side. It will be E3 into 1 upon minus Y3 into B3. Then I'll multiply with Y3 on both the sides. So it will be E3 into Y3, that is equal to Y3 upon 1 minus Y3 into B3. But Y3 upon 1 minus Y3 is nothing but capital Y3. That is E3 into small y3 is capital Y3 into B3. That means the term E3 into Y3 in this equation, it can be replaced with capital Y3 into B3. So in this way, for stage number 3, we have this relations. R2 into X2 is capital X2 into A. S30 into Ys is B3 into Ys. R3 into small x3 is A into capital X3. And E3 into small y3 is B3 into capital Y3. Now, with this, if I use these relations in equation 6, I will be getting X2 into A plus Y3 into B3, that is equal to X3 into A plus Y3 into B3. That is X3 into A, I can bring on this side. So it will be X2 into A minus X3 into A, that is equal to Y3, capital Y3 into B3 minus capital Ys into B3. Then A can be taken as common. So it will be capital X2 minus capital X3 is equal to cap A, that is equal to capital Y3 minus capital Ys into B3. That is A upon B3 is equal to Y3 minus Ys divided by X2 minus X3. Okay, so for stage 3, we have got this A upon B3 is equal to Y3 minus Ys divided by X2 minus X3. So on the XY plot, this is a straight line. This is equation of a straight line. Endpoints of this straight line are, one endpoint is X to capital X to Ys, whereas the other endpoint is X3, Y3. So if you call this as endpoint 1 of the line and this as endpoint 2 of the line. So in order to, we will rearrange the equation so that coordinates of point 2 are subtracted, or coordinates of point 1 are subtracted from the coordinates of point 2, corresponding coordinates of point 2. So for that we need to rearrange the equation. Therefore the equation is rearranged and you get this equation, minus A3 upon B3 is equal to capital Y3 minus capital Ys divided by capital X3 minus capital X2. So this is nothing but the operating line for stage 3. It passes through X2 Ys, it passes through point number 1 with coordinates x2, ys, and point number 2 with coordinates x3, y3. And slope of this line, slope of the operating line for third stage, it is minus a upon b3. Now let us plot this line on the xy plot. Let us continue with our previous graph. Now, since one end of the operating line is x2, ys, which is this point, the operating line for third stage should start at this point. So I'll draw the line with a slope of minus a upon b3. I get this line, I extend it to so that it intersects with the equilibrium curve, which is true for if under ideal conditions, if the stage is ideal. You please note every stage, each of the three stages is ideal, because the leaving, extract and raffinate phases, they are in equilibrium with each other. So we get this point, and the coordinates of this points are x3 and y3. So in this way, at the end of our calculations for stage 3, we get values of x3 and y3. So that completes our calculation for the third stage. And that completes our discussion for the 3-stage cross-current liquid extraction involving insoluble liquids, where A and B, they are not at all soluble in each other. So we need to plot the operating lines. Each of the operating line will have different slope. It may be having same slope. It depends on the amount of solvent that is used in the operation. So the objective of this analysis is to know the values of capital X1, capital Y1, capital X2, capital Y2, capital X3 and capital Y3. And I have told you how you can get those compositions. So with this, I end my discussion for this video. I hope you have understood how to follow the material balances for the 3 stages on this equilibrium diagram when you have 2 insoluble liquids. So in my next video, I will be discussing a numerical based on 3-stage cross-current liquid extraction. For now, thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it and hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. Thanks for watching. Have a nice day and hope to see you soon in my next video.